So let's begin the second part of chemical bonding. So it's a huge chapter. It will take some certain lectures to finish this chapter. So in the last lecture we studied about the Lewis octet rule and how each atom tries to complete its octet via bonding. So there are some exceptions and failures for octet rule. Let's just study them. First is hydrogen. So hydrogen has only one s orbit. So it has no need of octet to complete its valence shell. So it can just take one more electron and its 1s2 will be filled to get a noble gas configuration of helium. Second, according to octet rule, elements of group 1, 2 and 13 having valence electrons 1, 2 and 3 should not form covalent compounds because they have less than 4 electrons and cannot form octet by sharing electrons. But in reality, even the elements from group 1, 2 and 13, they do form covalent compounds. Example is BF3 and BEF2, which are both from the group 1, 2 or 13. So here you can see that central atom, these bonds are covalent bonds, and boron in this case has 6 electrons. So it has formed a molecule of BF3 via covalent bonds, but still it does not have 8 electrons. Similarly, for the second group, beryllium, we can see that it only has 4 electrons after sharing. So 2 of its own and 2 more after bonding. So in these cases, central atoms have less than 8 electrons. Then in some cases, the central atom has more than 8 electrons. So here we are talking about the groups which are 5th, 6th or 7 valence electrons. So for example, PCl5. So phosphorus normally has 5 valence electrons. So ideally it should only share 3 bonds to complete its octet. But it's sharing electrons via 5 bonds. So now it has more than 8. 1, 2, 3, 4, 5. So it has 10 valence electrons. Similarly, SF6. So it has 1, 2, 3, 4, 5, 6, 12 electrons. So sulfur normally only has 6 electrons. So it should ideally share only 2 electrons in order to form an octet. But here it is sharing all 6 of them and having therefore 12 electrons in its valence orbitals. So now we'll study the reason why this happens. So for PCl5 and SF6, where we saw that the number of valence electrons are actually more than 8. So one explanation was given by Sajan. So it says that considering singlet linkage, octet rule is still followed. So if we consider something called singlet linkage, and what it is a formed by donation of a single electron from an atom having an octet to another atom that is short of 1 electron to achieve the octet. So another atom that is short of 1 electron, example chlorine or example fluorine. So chlorine and fluorine has 7 valence electrons and they just need 1 electron. So in case of PCl5, you can see that phosphorus has 5 valence electrons and chlorine has 7. So 3 of these valence electrons of phosphorus are shared via chlorine with your normal covalent bonds, and the other 2, so this electron of phosphorus is donated by phosphorus to chlorine, and this electron is also donated by phosphorus to chlorine. So now chlorine has also 8 electrons and this electron is considered to be donated. So it is represented as this shape of half an arrow. So these are your normal bonds and these are the singlet linkages. So now if you consider that only 1 electron is being shared between this phosphorus and this chlorine, this phosphorus again has 8 valence electrons. Similarly, in case of sulfur also, if you draw a similar diagram, sulfur has a total of 6 valence electrons. So 2 are shared here, rest are 4. So these 4 are donated. So even though it's called donated, it will be shared between sulfur and phosphorus. So total number of valence electrons in sulfur would be 1, 2, 3, 4, 5, 6, 7, 8. So again the octet rule is followed if you consider a singlet linkage. One more explanation was given. It is Sidgwick's explanation for the same molecule PCl5 SF6. So Sidgwick talks about variable covalency. So in case of variable covalency, so we have already studied this before, but let's do it again. So in ground state, for example, sulfur has a configuration of this. So there is 1s2 also, 2s2, 2p6, but after that it's 3s and 3p. So this is the valence shell of sulfur. So we did not write the earlier configurations because when we are talking about bonding, we only consider the valence shell. So normally sulfur has 6 electrons in its 3s and 3p orbitals. So 3s has 2, 3p has 2, 1, 1. So here you can see that the normal covalency of sulfur is 2. Covalency is that how many electrons it can share. So it can share 2 electrons. So in ground state, it has only 2 covalency. But when one of the electrons get excited, so this 3p, in order to achieve some stability of half filled orbitals, this electron will jump to 3d shell. So now its valency is 4. One more can jump here and now its valency is 6. So if we consider this case of maximum covalency, variable covalency, sulfur can have a valency of 6 and therefore it can form a molecule of SF6. Similarly, we can draw that for PCl5 also. Polarity in covalent bonds. Between two dissimilar atoms possessing different values of electronegativity, this happens. So, for example, if we have a molecule which both the atoms are of the same kind, A and A, then this electron is equally shared between this electron pair is equally shared between both the atoms. But when the atoms are dissimilar, for example A and B, so obviously one of the two atoms will be more electronegative than the other atom. Electronegative is a tendency to attract the electrons. So in this case, this A atom will shift this electron pair towards itself a little bit, which will make this whole molecule as a polar molecule. When it does not happen, that is called as a non-polar molecule. So in this case, we can see that A has more electronegativity, and this bond is called polar covalent bond, or just polar bond, or partially ionic covalent bond. Why partially ionic? Because in case of pure ionic bond, this electron just gets into the A, so A gets a charge of -1 and B will get a charge of +1. But here the electron is not completely given to the A, it is still shared, but it's slightly moved towards A. That's why it's called a partially ionic covalent bond. So this gives a formation of dipole. So where in the case of dipole, this will have a partially positive charge, the one which is less electronegative. So in case of HF, example of HF, fluorine is much more electronegative than hydrogen, so it will pull the electron pair towards itself. So it will have a partially negative charge and hydrogen will have a partially positive charge. So this gives a formation of dipole. Now when we talk about dipole, we have another term called dipole moment. So we'll study this in electrostatics in 12th class in physics also, but just the basics we'll do now. It's a measure of polarity in covalent bond. So the more polar a covalent bond is, more charge will be on the electronegative element. So let's say this is the A, this is B. So this is more electronegative, so it has partially negative charge. So let's say -Q, and this has +Q. The distance between the two nucleus is R. So this is the representation, a plus and an arrow, and this arrow moves from positive to negative. So this gives the direction of dipole moment. So dipole moment is obviously a vector quantity. It has a direction and it has a magnitude. So what is the magnitude? It is Q into R. So Q into distance between the two atoms. So dipole moment is QR and its direction is from positive to negative, and it's represented by this symbol. So it's called a crossed arrow symbol. It's a vector quantity. It's represented by symbol mu, and its unit is dBi. 1 dBi is 10 to the power minus 18 ESU centimeter. So don't worry about this terminology, just remember this. 1 dBi is 10 to the power minus 18 ESU centimeter. So dipole moment and molecular structure. So dipole moment helps us in arriving at the molecular structure sometimes. For a simple example, if there is no dipole moment, we can assume that it's a diatomic gas. And if there is a dipole moment, we can calculate that, and then we can, with some calculations, we can find out what is the molecular structure of that molecule. So net dipole moment of a molecule is resultant of vector sum of dipole moment of all polar bonds in a molecule. So we already studied about vector sum in physics. So here a molecule can have different more than one polar bonds. For example, in case of water, so you will have this is your water molecule. So oxygen is more electronegative, so here it will be delta minus delta plus, and here for this bond again it will be delta minus delta plus. So in this case the dipole moment will be in this direction, and for this bond it will be this direction. So the net dipole moment of this molecule will be the vector sum of these two vectors. So molecule geometry can be decided by measuring mu of the molecule. So if we can measure the dipole moment of this whole molecule, then we can individually find by the simple geometry that what will be the dipole, what is the angle between these two. So if let's say this is theta, so if we know this individual one, dipole moment of this OH bond, so that cos theta plus this cos theta will be the final dipole moment. So from that we can find the theta of the half angle between the H2O molecule, and double of that will be the full angle between the HOH. So we can find out the geometry of water molecule via dipole moments. So example, diatomic molecule. So in case of HF, for example, mu is found out to be 1.9 dBi. For HCl, it is found to be 1.03 dBi. So why this is more than this? Because fluorine is more electronegative than chlorine. Also fluorine molecule is smaller than that of chlorine. So it has more tendencies, this nucleus has more tendency to attract the electron pair. So these two reasons, because of these two reasons, the dipole moment of HF is more. So higher the difference in electronegativity, higher the mu. Triatomic molecules, so BeF2. So BeF2 gives a total dipole moment of 0. That gives us an idea of the geometry that it is a straight line. That's why the vector sum is total 0. For water molecule, it does not come out to be 0, and as we discussed before, here we can find out that the net dipole moment will give us an idea of how much is the angle between HOH. Tetraatomic molecules, so example BF3. So this is exactly 120 degree angle between each of them. So how do we know that? Because when it was calculated, the mu came out to be 0. So we know that BF bond is a polar covalent bond, and still mu is equal to 0. That means the molecule geometry must be like this. For NH3, so nitrogen has an electron pair, and then it has 3 more electrons which it shares with the hydrogen. So here again the dipole moment was found to be in this direction. It will be the vector sum of all these 3 individual dipole moments. So when we draw NH3 like this, so dotted means it's going inside the plane, and this triangle, solid triangle, means it is coming out of the plane. So this is just a representation that it means different planes. So ionic bond can be regarded as extreme case of polar covalent bond. So just like we could say that the polar covalent bond is slightly, it's a polar ionic, partially ionic bond. So we can also say ionic bond is an extreme polar covalent bond. So in extreme case, the electron will be completely taken up by the more electronegative atom. Covalent character in ionic bonds. So LiCl is ionic compound but is more soluble in organic solvents than water. Solubility in water is a feature of ionic compounds, but LiCl, even though it's ionic, it is more soluble in organic than water. So in water, ionic bonds normally get dissolved in water, but LiCl does not. The reason is the LiCl itself acts a little bit as a covalent compound. Why? Li is very small atom, so its cation will be very small. Cl is quite big, which will be the anion. So here again, being the smaller in size and having an already positive charge on it, since it's an ionic compound, this will pull the electron cloud of chlorine a little bit towards itself. So it's important to remember that it's this partially negative charge which is coming is through the electron cloud of only chlorine. There is no concept of shared electron here. So it has already given its electron to chlorine, but now the electron cloud of the chlorine is slightly pulled towards the cation of Li because it is very small in size. So this gives rise to a polarized anion. So cation attracts the outermost electrons of anion and repels its nucleus. This distortion in anion causes the electron density to shift towards cation, resulting in some sharing of electrons between the two. This phenomena is called polarization. And the polarized molecules, they are more soluble in organic solvents. Fazan's rules regarding polarization. So just some factors on which the polarization depends. Size of the ions, smaller the cation, larger the anion helps. That's why LiCl is more polarized than NaCl. Charge on ions, larger charge on both ion helps. So AlCl3 will be more polarized than MgCl2 than NaCl. Electronic configuration. So cation with the S2p6d10 polarizes more than the cation with S2p6 as d subshell shields nucleus less. So we already studied in our atomic structure that d orbital, the electrons of the d orbitals are not that close to the nucleus, so they do a poor job of shielding the outermost electrons. So cation in that case will be able to attract more the other electrons if the outermost shell is d. So the cation which has this configuration, which has d configuration at the end, it polarizes more than cation with S2p6 configuration because they can shield the cation, the nucleus more. As d subshell shields the nucleus less. So CuCl is more polarized than NaCl because this is the configuration of CuCl. So these electrons do a poor job of shielding the nucleus. So the nucleus of copper, it has more charge than the nucleus of sodium, and because of the poor shielding, it has a more attractive power than the sodium. Dielectric constant of the medium. So if the whole molecule is kept in a medium, dielectric dilutes the polarization. So more dielectric means less polarization. So what happens that dielectric itself has a potential to develop into a partially positive and partially negative charges. So whatever is the medium of the dielectric, it does that. It is polarized itself. So then that, for example, if this is Na plus and this is Cl minus, so what happens that the O, oxygen, as a dielectric, it will come near this Na plus, so it will surround this Na plus molecule, and therefore this surrounding by and this H plus, delta H plus, will surround the chlorine. So this dilutes the actual polarization between the Na and Cl atoms. So more dielectric means less polarization. Coordinate covalent bond. So it's also known as dative bond. So it's a special case of covalent bond where electron pair is completely donated by one electron. So in singlet linkages, we saw that only one electron was donated. Here, two are donated to the acceptor. So we have A and B. So this is the symbol that this complete arrow means the two electrons are donated by this A to the B. So since the electrons are donated here, B will have negative charge, A will have positive charge. So again, just like dipole, the angle of this arrow is from positive to negative. So you can think of it like from where the electron is donated to whom, in that direction the arrow will be. So this is A, this is B. So eventually it looks like this. So there is no difference. Once donated, it behaves exactly like covalent bond. That is, the electron pair is shared equally by both atoms. So let's see some examples. Ozone. So ozone, the symbol is like this. So now you can guess that these two electrons will be shared normally, and here one electron pair will be donated to this oxygen. So now you can see that octet is completed for all three oxygen molecules. So this electron pair belongs to this oxygen molecule. So again, this will have a plus charge and this will have a minus charge. SO2, SO3. So oxygen and sulfur are of the same group, so their structure is little bit different. I mean, sulfur has SO2 and SO3 both. So SO2 will have the same structure as ozone, and SO3 will be sharing two electrons here and will be donating its two pairs to two oxygen molecules. Some more examples. NH4 plus. So nitrogen has 5 electrons in its valence shell. So normal covalent bond. So one is given here, one is shared here, one is shared here. So 3 are shared here. It is left with 2. So both of them are donated to H plus. H3O plus. So H2O is already a stable water molecule. So now the oxygen is left with 2 more electron pairs. So one of them is given to H plus. H2SO4. So sulfur again has 6 valence electrons. So 2 are shared here. It has 4 more left. So one pair is given here, one pair is given here. HNO3, nitrogen has 5 in its valence shell. 1 is here, 2 are here, one pair is left, which is given to oxygen. H3PO4, so phosphorus same as nitrogen has 5. So 3 are bonded here, one pair is left, which is given to oxygen. So these are very basic atoms, sulfur, nitrogen, phosphorus. So if you know their valencies and all covalencies, so it will be easier for you to, you don't need to remember this. Once if you know the covalency of phosphorus, you can directly draw this structure. Hydrogen bond. When hydrogen atom is bonded to a highly electronegative atom. Okay, let's first understand directly from the figure and then we will read the definition. So we have an HF bond which is polarized. We already saw that. So F being more electronegative will have slightly negative charge and H will have slightly positive charge. Now when various molecules of HF are brought together, this slightly negative charge is attracted to the slightly positive charge of H. So this weak bond which gets formed between the partially negative of one molecule to the partially positive of another molecule is called as hydrogen bond. So important thing to note here is hydrogen bond forms between two different molecules. Till now we were studying that the bonds within the same molecule. So here hydrogen bond is between two different molecules. So when hydrogen atom is bonded to a highly electronegative atom through covalent bond, highly electronegative one shifts the shared electron pair to its side. So we are talking about HF, resulting in partial negative charge on it. and partial positive charge on hydrogen. Now, partial positive hydrogen atom of one molecule may attract partial negative electronegative atom of some other molecule. This weak force of attraction is called a hydrogen bond. So it can be some other molecule, it can be any molecule, it need not be the HF only. So it can be HF and water, like that. So the factors which help in that is, first is high electronegativity. So HF is will be more inclined to form a hydrogen bond than HO, then HN. So F is more electronegative, so this will be more polar. So more polar means greater chances of forming this delta minus and delta plus. Therefore, this hydrogen bond will be much stronger. Smaller electronegative atom. So the atom which is electronegative should be smaller. So the size of the atom. Examples of hydrogen bond. So intermolecular. In this case, the molecules are same. So HF, for example, we just studied. So its structure is like this. Water. So it has this kind of structure, kind of self-explanatory. NH3, it has like this. Ice, that is also intermolecular, but it's a tetrahedral 3D structure. It's difficult to draw here. So just know that the structure is different than normal water. The structure actually is not as closely packed as water, and that's the reason that ice is lighter than water. Normally solids are more densely packed, but in case of ice, the structure is different, very different than normal water molecule, and therefore it is lighter. Intermolecular, again, one more example is C2H5OH plus water. So intermolecular means that it's between two different molecules. Same molecules or different molecules, but two molecules should be present. So it can be that both are same, it can be that they are different, but this bond exists between two different molecules. So example is ethanol plus water. So it looks like this. This H of ethanol is hydrogen bonded to this oxygen of water molecule, and again this hydrogen atom is bonded to the oxygen of this ethanol molecule. So these are examples of intermolecular. There is one more kind of hydrogen bond which is intramolecular. So it's the same molecule, within the same molecule this hydrogen bond exists. So you can see from this figure that this oxygen and this hydrogen, they have a hydrogen bond between them. So it allows them to complete this hexagonal shape. Because of the hydrogen bond, the features of the compounds which have hydrogen bond: high melting point, boiling point. So obviously that now that we have more bonds, the boiling point and melting point will be more. The reason that some of the gases become liquid, for example water is liquid, and H2S, even though sulfur and oxygen are of the same group, water is liquid and H2S is gas, because the hydrogen bond in water, they make it liquid. So in H2S, the sulfur is not that electronegative, so hydrogen bond doesn't form. Therefore H2S is able to escape as different molecules, which is a gaseous form. Soluble in water. So water itself belongs to the polar molecule. Water is a polar molecule, so other polar molecules, when put into the water, they will bond with the water molecules, and therefore they will dissolve in water. So this is an example of that, solubility in water. Van der Waals forces. Short-lived electrostatic forces that exist between all kind of atoms, molecules and ions when they are brought sufficiently close together. For example, if two polar molecules are brought together, they will have some interaction, some attraction between them. So they are called dipole-dipole interaction, also called as Keesom forces. So hydrogen case is a special case of that, where we only talk about hydrogen bond, which is partially polar. Here it is for any dipole, so dipole-dipole interaction. So if two dipoles are the molecules which have some dipole moment, they are brought together, then this weak interaction force between them will be the Keeson force. Dipole induced dipole interaction. So if one dipole, one molecule which has some dipole moment is brought to a neutral atom, so it will distort this neutral atom into a partially negative and positive charge. So this plus will make this molecule also a little bit of dipole, not as strong as this, but a little bit. So this is your permanent dipole, and this will be called as induced dipole. Temporary dipole moment induced dipole interactions, also called as London forces. So here, even in the case of your normal diatomic gases like H2 and O2, some nuclear displacement which is random will cause a molecule to form a dipole, and it can be in either direction. So these are in equilibrium. This sign means they are in equilibrium. So they keep shifting randomly between all these forms, and when they are in this form, they will for some time they will have an attraction towards the different molecule, which will probably have a plus charge near to this negative charge, and like that. So it's a temporary induced interaction. The reason is slight random displacement of nuclei. So if nuclei displaces slightly to the right of a molecule, let's say, then it will form a dipole like this. If the nucleus just slightly moves to the left, then it will give formation of this dipole, and if it's in the center, it will be this. So all these three are very rapid, and they are very short-lived, and that's why they are temporary. Factors on which van der Waals forces depend. Temperature: higher the temperature, less intermolecular interaction, and therefore less van der Waals forces. So when you increase the temperature, they will just randomly move from here to there, and therefore they won't be able to interact that much with each other. Pressure: high pressure means the molecules are brought closer together. That means more van der Waals forces. Number of electrons present in molecules. If the electrons are more, the chances of diffusion of electron cloud is also more. That means polarization will be more, and again more van der Waals forces. Molecular size. So this and this are kind of similar. If number of electrons are more, and then the van der Waals forces are more. Similarly, if molecular size is more, then also the molecules are easily polarized. Therefore, it will have more van der Waals forces. Effects on properties. So here are some of the outcomes of van der Waals forces. Melting point and boiling point is increased. So certainly the more bonds means it's difficult to break those bonds, and therefore the boiling point and melting points are more. Hardness is less. Liquefaction of gases. So gases, just like we saw in the example of your water, so because of the hydrogen bond, it is become liquid. So similarly, the normal gases also, even the oxygen and nitrogen and hydrogen, so when they are pressurized and the temperature is decreased, they become liquid. The reason is these forces, van der Waals forces, as you drop the temperature and you increase the pressure, the more van der Waals forces they exist between them. So even if they are diatomic gases, so at one point they will start forming the bonds quite stronger to change the state of the gas. So state of gas will become from gas to liquid. Deviation of ideal gas from real gas. So in ideal gas, we assume that there are no intermolecular interactions, but in reality they are, and that's what are van der Waals forces. So that is the reason for the deviation of ideal gas. So we'll study about this more in the next chapter. Joule-Thomson cooling effect. So what happens is when you have a pressurized gas in a container and you put a hole in that container and the gas is released through that small orifice, the temperature of that gas drops. So why that happens is we have those gas molecules here who are connected through some bond, which is van der Waals forces. So when they are escaped, that means the bonds are breaking. So if the bonds are breaking, that means they are taking certain energy from somewhere, then only they can break. So that energy is taken from the heat. So it absorbs the heat, and therefore the cooler gas will come out. So once again, there are bonds. No, we won't call them bonds, but some van der Waals forces between the different molecules in this pressurized gas. Now when the pressure is dropped, then now we have less of those bonds. So in order to have less bonds, the gas has to absorb some energy to break those bonds, and therefore the gas which is now getting released, it will have less temperature because it has lost some heat. Or you can think it conversely. If you have a gas here and it's supposed to form some bonds between that, you have to give it some energy. In that case only the bonds will form, because those bonds will have some energy stored within them. So that's the end of this lecture.